In the last lecture, we derived Legendre's equation for from the Laplacian in spherical polar coordinates. Well, here we're going to see how it fits into the Schrödinger equation, where we're time-independent Schrödinger equation, which is what TISE stands for an electron-proton system with reduced mass mu in a Coulomb potential here. So the Schrödinger equation is h bar squared over 2 mu, and this here is the del operator squared plus this potential, and equals the energy wave function, or likewise written out in full. The Laplacian was defined before, so separating variables, inserting and dividing by r rho theta, r theta phi, and multiplying by r squared, we will come up to this equation here, plus 2 mu r squared over h bar squared e plus, and this is the Coulomb potential, which equals 0. Now the phi must be constant, so we set 1 over phi, the second derivative of phi equals minus m squared, which will give us solutions of e to the I m phi, where m is contained in the integers, as I believe we previously established. Now we're renaming the theta and r parts. The remaining theta and r parts must separate. So the theta part depends on theta, and the r part only depends on r. So each is equal to the same separation constant. Here the theta part is minus L plus 1, where which is here is, sorry, I've put it into into the equation here. So this is the probably the most what's the word, a most recognized form, and the radial component is here. So and instead, like we said, this is the minus LL plus 1, which equals 0. Now the angular equation is the associated Legendre, where x equals cosine theta, y of x equals theta. So this is 1 over sine theta d by d theta, sine theta theta prime equals d by dx 1 minus x squared y prime of x. So we come to, again, this Legendre's equation, but for now it's for the hydrogen atom for our purposes here in the Schrödinger equation, which these steps I've pretty much been through before, but I'm going to keep going through this because I think it's really important these concepts are drilled into your head. This is probably arguably the most difficult thing you'll come across, you'll come across in atomic physics, is deriving these equations. But once you fully understand these and how the spherical harmonics and the radial terms work, then much of atomic physics will be fairly straightforward from then on. You'll have shell model and spectroscopic notation and whatnot. But anyway, moving on. So for m equals 0, this reduces to Legendre equation here. Regularity theta equals 0 and pi means L equals 0, 1, 2, ... And the magnitude of m is less than or equal to L. So the angular solutions are the spherical harmonics here, whose NLM is a normalization constant, which is given here. This is derived by using Legendre's, I think it's, what is it called? Rodriguez formula, I think this is defined by using that here. And these are Legendre polynomials, which I'll discuss this next.